This is video number 91 in our series on tensor calculus. In this video, we're going to derive the Frenet formulas. The Frenet formulas can be used to define an orthonormal basis that is roughly equivalent to the tangent space we developed while working with surfaces. This is an equation we developed back in video number 76. It's how we defined the principal normal. Well, it's also one of three relationships which collectively are known as the Frenet formulas. Now we know from video 76 that our unit vectors here, s hat and p hat, are orthogonal. They're perpendicular to each other. Well, let's remind ourselves of how we know that. Suppose we have some vector v that is constant in magnitude, can vary in its direction, but its magnitude is fixed. Well, that means that the dot product of v with itself has got to be some constant. Okay, so now let's take the derivative of both sides of this equation with respect to s. And of course, to do that, we need to use the product rule. The dot product is a commutative operation, so these two terms are equal. Therefore, that leads to the fact that dv ds dotted with the vector itself has got to be equal to 0. So any vector is orthogonal to its derivative if its magnitude is constant. That's a general property that we can make use of over and over again. Okay, so up here what we'll do is we'll take the dot product of both sides of this equation with s hat. Well, s hat is a unit vector, so it's constant in magnitude. So when we dot the left side with s hat, we're going to get 0 because of this relationship here. And we can take the dot product with the right-hand side, and because it's equal to 0, we can divide out this factor k. So on the right-hand side, we're going to get p hat dotted with s hat. And this proves the point, that the dot product of these two vectors is 0, and that means they're orthogonal. Well, now let's take the derivative of both sides of this expression with respect to s. And of course, again, we have to use the product rule. Well, now let's consider this second term right here. We can replace this factor with our definition that we have for this expression up here. So this becomes p hat dotted with kappa p hat, which of course can look like this, kappa times the dot product of p hat with itself, and being a unit vector, that means that this term is just 1. Therefore, this is equal to our curvature, kappa. Well, we can also express it this way, kappa times s hat dotted with itself, and we can do this because the dot product of s hat with itself is just 1, so we're just multiplying by 1 here. And then this is equal to kappa s hat dotted with s hat. So this term right up here can be replaced with this form. So all I've done is to replace this term with this one as per the analysis we did right down here. Okay, well now because the dot product is distributive, we can factor out this factor of s hat. So what we have here in this factor is a vector quantity. It's two vectors added together, so this is going to be a vector. Well, this new vector that we've come up with here, dotted with s hat, is equal to 0, and that tells us that the new vector quantity here is orthogonal to our unit tangent vector. Well, let's look at something else. Suppose we dot this new vector with p hat. Well, when you dot the first term here with p hat, we have the condition we talked about a moment ago. We have a vector p hat which is of fixed magnitude dotted with its own derivative. That means that Dotting this with p hat will give us a 0 term. And then we already know that s hat and p hat are orthogonal. We dot p hat with this term, it'll go to 0. So if we form the dot product with this new expression with p hat, and we get a value of 0, that means that it's also orthogonal to p hat. So we have a vector quantity that is perpendicular to both the unit tangent vector and the principal normal. Well, this leads to a new definition. We're going to say that the derivative of p hat with respect to s plus the curvature kappa times s hat, this new expression right here, is all going to be equal to a new scalar factor of tau times a new unit vector q. Okay, well, next we're going to subtract this term from both sides of the equation. What we have here is the second of the three Frenet formulas. So let's define the two new objects that we've got right here. Q is a new unit vector, and it's known as the binormal vector. Tau is a scalar factor that represents the magnitude of this vector, and it's known as the torsion. Well, let's remember what we said just a minute ago, that this vector right here that's now represented this way is orthogonal to both s hat and p hat. Well, that in turn means that this new unit vector, this binormal vector, is then orthogonal to both p hat and s hat. And of course, p hat and s hat are orthogonal to each other. In other words, what we have now is a set of three unit vectors that are mutually orthogonal. And because they represent an appropriate orthonormal basis for our ambient space. We can use these three unit vectors as the basis for any vector that we want to represent in the ambient space. In that sense, these three vectors define a space that is roughly equivalent to the tangent space we defined when working with surfaces. Okay, so we've got these three unit vectors, and they're mutually orthogonal. So let's say that s hat is pointing to the right here, like this. This is our unit tangent vector. And then the principal normal is pointing back here like this. Okay, when we say that these vectors are all going to be mutually orthogonal, that leaves us with two possibilities. Q hat can either be orthogonal in this direction or in a downward direction like this. So what we're going to do is to include as part of our definition here that Q hat is going to be defined as the cross product of S hat and P hat. Now, according to our diagram over here, that means, using the right-hand rule, that Q hat is going to be a vector pointing in this direction right here. Now, we could have defined it such that Q hat is equal to P hat crossed with S hat, which reverses the sign and points this unit vector in the direction going downward. Now, these are equivalent in the sense that to represent the vector in either one of these, we just reverse the sign of the torsion. So what we're saying is that part of our definition is to choose the sign of the torsion in such a way that this condition is met. Okay, so the next thing we want to do is to take the derivative of both sides of this expression with respect to s. And to do that, we're going to need to use the product rule over here on the right-hand side. Now, the product rule works for cross products exactly the same way it does for the dot product. Next, we want to replace this term with its equivalent as per the first Frenet formula. In other words, this is equal to kappa times p hat. And we also want to replace this expression with this one up here. Okay, so what I've done is to replace this term with this one, and I've replaced this term with this expression. Okay, let's expand this out now. And what we'd have is dq hat ds being equal to, first of all, this term. I can bring the value of kappa out, and we're left with p hat crossed with p hat. And then over here, I'm going to use the distributive property to distribute s hat into these two terms. So the first one will give us a negative kappa times s hat crossed with itself. And then when I distribute this to the second term, I'm going to get the factor of tau times s hat crossed with q hat, like this. All right, well, any vector that is crossed with itself is going to be equal to 0. So this has got to be equal to 0 because it's the same vector. Same is true right here. And here, if we look up at our diagram, the cross product of s hat with q hat using the right-hand rule would produce a unit vector pointing out of the page like this. So this is equal to negative p hat. And that means that our final expression here is the derivative of q hat with respect to s. And that's just going to be equal to the only remaining term here, which is negative tau p hat. And this then becomes the third and final Frenet formula. All right, having developed these three Frenet formulas, let's go see how they apply to our sample curve. In the last video, we derived the curvature and principal normal for the spiral. So let's move on and derive the binormal vector and the torsion. Well, the first thing we've got to do is to find the derivative of our principal normal with respect to s. So we start by finding the derivative of this expression with respect to t. That's a lot of work, but here's what it looks like. So the derivative of this item with respect to t is this expression. And to consolidate it, I've used the values of a and b here, which are expanded out down below. So this is a and this is b. It would be too much for me to expand all that out in one expression. Okay, but what we really need is the derivative of our principal normal with respect to s. So given the derivative with respect to t, we can get that just by including this additional factor right here. Remember that 1 over the square root of u is equal to dt ds. All right, and so that factor right here means this is just the chain rule. So adding this factor takes us from here to here. And the effect of adding this additional term is just to include this additional factor in the denominator. Next, we've got to take the curvature, that's this expression right here, and multiply that by the unit tangent vector. So we'll go back up and get that. That's this expression right up here. So we're going to multiply those two together, and then we're going to add that product to the derivative of our principal normal with respect to s. So we're going to add that product to this expression right here. When we do that, that's what we're going to get right here. So again, we've taken the product of the curvature and the tangent vector, unit tangent vector, added that product to the derivative of p hat with respect to s. Now that involves a lot of algebra. You have to do some multiplication, collection of terms, find a common denominator. Again, you have to do some multiplication, collection of terms. But when all the dust settles, this is the final expression. And again, I've had to factor some things out here for the purpose of space. I've got x, y, and z this time. and those values are represented by these polynomials down here. So it is quite a complex expression and takes a lot of work, but this is the result you'll get if you follow through with all of those steps. Okay, we're almost done here. What we've got now is a vector represented by this product. So we need to split these out and find out what each of these individual components are. Well, tau is simply the magnitude of our vector. So to find the magnitude of any vector, you take its dot product with itself and then take the square root of that. So here, to find the magnitude of this expression, we need to square this term, square this term, square this term, add them all together, divide by the square of the denominator, and then take the square root of that result. And when you do, this is what you're going to get. You perform that operation I just described, this is going to be the result. It's a scalar value, and it is the magnitude of this expression right there. Okay, and finally, to find the value of q hat, we simply divide this expression by this. We're dividing this expression by its own magnitude, and that's going to give us the unit vector itself. And of course, in the process of dividing one by the other, these two terms are going to cancel out, and the result is going to look just like this. So here is the binormal vector, and here is the torsion. All right, well, there's a lot involved in doing that, and I wouldn't blame you at all if you didn't follow through with all of those steps. I have to admit that it took me the better part of a day and a half to compute all these results for the demo. But if you're stranded, marooned on a desert island somewhere with a ream of paper and 15 or 20 sharp pencils, you might find it interesting to take the time to validate my results here. Okay, but at least go through and, again, as before, study it long enough to make sure you understand the process. Well, let's move forward and see what this looks like then in our demo. In the last video, during the spiral demo, we displayed the two unit vectors, s hat and p hat. S hat, of course, is the unit tangent vector that's always tangent to the curve. P hat is orthogonal to that one and is associated with this scalar value known as the curvature. The curvature is a measure of how quickly the direction of s hat is changing as the point progresses on the curve. Well, in this video, we've derived another unit vector known as the binormal vector, and we'll display that here. It's q hat. And q hat is also associated with a scalar value, and we call it the torsion. So this is the scalar value of the torsion. And while the curvature is a measure of how fast the direction of s hat is changing, the torsion is really a measure of how fast the direction of p hat is changing. If you look at it from behind, as this point progresses up the curve, p hat will actually turn in sort of a clockwise direction. And so tau here is a measure of how quickly p hat is rotating, and that's why we call it the torsion. Now together, these three unit vectors define an orthonormal basis that allows us to represent vectors in any direction. And so we can set up three different planes, one here, one vertical this way, and one vertical this way. And so we have these three intersecting planes that are at right angles with each other. So let me just put it in motion now. And you can see as our point moves on the curve that at every point on the curve we have an orthonormal basis that can be used to represent a vector in our ambient space. Okay, well, back in video 88, we made the point that although we're going to illustrate everything in 3 dimensions, everything we were going to do for curves would work equally well for higher dimensions. So let's go talk about how the Frenet formulas work for higher dimensions. Here we have the Frenet formulas as we see them normally written. First thing I'm going to do is to rename the components a little bit and do some restructuring. So this set of equations is exactly the same set of equations as this, but what I've done, I have renamed our unit vectors SP and Q as T sub 0, T sub 1, T sub 2. I've also renamed our scalar factors kappa and tau as kappa 1 and kappa 2. I've also swapped the order of these two terms and moved this guy over a little bit to this position. You'll see why in just a minute. So having restructured this, I'm now in a position to show you a pattern that's going to work for any number of dimensions. Now I don't have the time to prove any of this, I'm just going to show you the answer. So let me show you what our solution looks like for 4 dimensions. With 4 dimensions, we add an additional equation. The first two are exactly identical, as you see, but the third one looks a little like this, but it has this extra term in it. And then the fourth equation looks like this one, except the index values have been bumped up like this. Okay, so what I'm going to tell you is that T1 is orthogonal to T0, T2 is orthogonal to T1 and T0, T3 is orthogonal to T2, T1, and T0. So this is a pattern that's going to work for any number of dimensions. And as I say, I don't have the time to prove it, but this will provide an orthonormal basis for a 4-dimensional Euclidean space. Okay, well let's see what it looks like then for 5 dimensions. To find the solution for 5 dimensions, we just extend this pattern one more time, and it looks like this. So here we now have 5 unit vectors, T0 through T4. They're all mutually orthogonal to each other, and will provide an orthonormal basis for 5 dimensions. Okay, the best way to show how this works in general is to represent it as a recurring formula. So let me show you that. The general solution looks like this. The first equation is always this. The last equation always looks like this, just plugging in the appropriate value of n. And then all the equations in the middle will take this pattern. If you'll follow this pattern, iterate through it with values of m from 1 to 3, you'll see that this pattern produces these 3 equations right over here. So the general solution takes the form of a recurring formula. Now if you're interested in a proof that this solution works, you'll just have to research that on your own as an advanced topic. We just don't have the time to cover it here. What we've done in this video is to derive what we call the Frenet formulas. Now, given our knowledge of our unit tangent vector and the principal normal, we were able to define yet a third unit vector that is orthogonal to both of these. And together these 3 unit vectors provide an orthonormal basis that lets us represent any vector in the ambient space. We then went on to show that these formulas are really part of a larger pattern that can be used for any number of dimensions. So if we apply this recurring formula, we can develop a set of n unit vectors that form an orthonormal basis for an ambient space of any number of dimensions. This orthonormal basis relates to curves the same way that the tangent space relates to surfaces. We can use it to define vectors that point in any direction in the ambient space. As we finish up, I need to make one final point. All these relationships are based on derivatives with respect to the arc length S, and as such, one might reasonably question whether they are valid tensor equations. Well, the answer is yes. So let me show you how we know that. Well, you've seen this relationship before. The derivative with respect to the arc length S of any object that is invariant, such as S hat, can be broken down into the chain rule like this. And we know that this factor is equal to 1 over the square root of u. 1 over the square root of u is equal to the Levi-Civita symbol with an index in the upper position. And this derivative of an invariant object is the same as the covariant derivative. So that having been said, we could replace this with this form, and we can do the same thing for any of these relationships across the board. And that means that we're dealing with an invariant expression in each case. We have a fully contracted expression here. There's only one index, and it's a dummy index. There are no free indexes. So all of these relationships are, in fact, invariant relationships and can very easily be adapted to any coordinate system by replacing them with this form right over here. So they are indeed valid tensor equations. Now at this point, we've completed a pretty thorough analysis of how surface manifolds and curve manifolds are embedded in a three-dimensional Euclidean ambient space. Well, what we're going to do in the next video is to shift gears and take a look at how curves are embedded in a two-dimensional surface.